Hi students, this is A. Srinivas, lecturer in physics, Vignan Junior College. Students, we are discussing moving charges and magnetism chapter. In this video, we talk about the following concepts. First of all, we would like to find the magnetic field due to long solenoid. Solenoid is a very important device nowadays to produce magnetic field. So here today very first we calculate the magnetic field along the axis of solenoid, long solenoid, as well as magnetic field due to solenoid of finite length, second one, and magnetic field due to toroid, and third one, the last one is the numericals, problems belongs to this explained concept. So in day-to-day life, nowadays, to produce electromagnetic waves or to operate TVs as well as radios, we must require magnetic field. That magnetic field is now we are producing in electromagnetic way, not by using permanent magnets. Now we are producing, in most of the cases, magnetic field is generated by electromagnets. Here the solenoid is a very good electromagnet. By passing the current through the solenoid, we produce magnetic field in the solenoid. So before knowing about the solenoid, we evaluate magnetic field due to long solenoid or magnetic field due to finite length solenoid or magnetic field due to toroid. All these expressions will be derived by using Ampere's law. Already we discussed the Ampere's law in previous part of our discussion. So let me recall the Ampere's law and then we go for our present derivations. So Ampere's law. The equation form of Ampere's law is this one, and this is read as, so line integral of magnetic field along any closed loop. Line integral of magnetic field along any closed loop is equal to mu naught times the net current passing through the closed loop. Here, let me understand this formula by using this animation. Let this be a current carrying wire. Here students, let this be a current carrying wire, carrying current I naught. Consider a closed loop around it. Here we are assume a closed loop around it at certain radius r. Then there is a magnetic field along this closed loop. Here I am redrawing the loop. Along this closed loop, take the line integral of magnetic field. Line integral of magnetic field along the closed loop. Line integral of magnetic field along the closed loop is equal to mu naught times the current. This is the current carrying wire here. So net current passing inside the closed loop is mu naught. So line integral of magnetic field along closed loop is mu naught times net current passing through it. And this is the very good expression by using this Ampere's law. In today's video, we derive the expressions for magnetic field of solenoid and toroid. So let us move on to the first discussion, that is magnetic field due to solenoid. So here we would like to find magnetic field due to solenoid. First one, magnetic field due to long solenoid, then we made our discussion. So I would like to change the pen now. Pen color. Here to find the magnetic field due to solenoid, here let us consider a solenoid. Solenoid is a wire wounded on a cylindrical shaped material. This is a cylindrical shaped non-conducting material. Students, first we consider a cylindrical shaped non-conducting material. In the diagram, we are observing a cylindrical shaped non-conducting material. Okay. Here, let us see the animation, students. Look into the animation. Once again, here closely observe we have a non-conducting cylindrical shaped object around which a conducting outside insulated, inside is conducting, outside is insulated. So outside insulated, inside conducting wire like copper is circulated around the solenoid on its surface. See the animations in which there is a copper conducting wire is wounded, and we connect this copper conducting wire. The two ends of the copper conducting wire are connected to the battery, so that see the current in this direction, the current is passing through the circulated wire. Through the circulated wire, current is passing. See the animation. In this way, the current is passing through the wire. Here, students, once again I repeat the structure of solenoid. We have a cylindrical shaped solenoid, cylindrical shaped non-conducting material, which is denoted by the violet color object on the screen, and outside copper and inside conducting material like copper is wounded. Number of turns are wounded as shown in the diagram, and we connect the two ends of the wire to a battery so that current is circulating. Here, students, you must understood the wire is wounded like this. So in anti-clockwise direction. For this view, when we view from the other side, the current is traveling in anti-clockwise direction like this. So anti-clockwise direction. For this, for each loop, when current is passing through the loop, there exists a magnetic field along the axis of the loop. We know that. Already we discussed about magnetic field along the axis of current carrying loop. As current is circulated and passing through the loops wounded around this cylindrical object, there is a magnetic field along its axis. So see, you are observing the animation. So once again, with the animation I would like to explain the solenoid. In solenoid, first of all, we have a cylindrical non-conducting object, and a conducting wire insulated outside is wounded like coils around the cylinder. Observe them in animation, and we connect the two ends of the conducting wire to a battery so that the current is traveling. As shown in the diagram, you are observing it. A current, here current passes into the wire and comes out of the board. Here current passes into the wire and comes out of the board. In that way, current is passing through the wire. Because each one is a loop, each circulated wire around the cylindrical object is a loop. So current carrying loop must produce a magnetic field along its axis. There is a magnetic field. For this side observation, the current appears to be traveling in anti-clockwise direction, so the magnetic field is along this direction. So see the direction of magnetic fields in the following animation. See the arrow marks, observe, look into the animations in this direction. So here B bar is like this, such that this face becomes north pole and this face becomes south pole. Look into it. So the right side face becomes north pole and the left side face becomes south pole, such that this solenoid now behaves like a short bar magnet. Short bar magnet produces magnetic field, a permanent magnet. Equal to that, this solenoid means a conducting wire insulated on cylindrical object and current passes through them, then magnetic field is produced along the axis. Here, along the axis, this is the magnetic field. Here, don't consider, by looking to the diagram, don't consider there is a magnetic field outside the region. Here there is magnetic field inside. The magnetic field direction is circulated like this at this point. These are the direction of magnetic field. In this way, the magnetic field loops are circulated. So, students, as I explained, this becomes north pole and this is south pole. That is also important. If our point of view from right side, if current is traveling in anti-clockwise direction, rotate your fingers in the direction of flow of current. This thumb indicates the north pole, hence this right side of the solenoid becomes north pole and left side becomes south pole. Students, I would like to show an animated video on the solenoid, then you feel a good experience by looking to this video. So let us see the video of the solenoid, students. Here in this video, that's what already explained about the structure of solenoid and development of magnetic field along the axis of the solenoid by using an animated presentation. And similarly, here we are going to see an animated video of solenoid. It gives a very well experience for you. So look into this video of solenoid and its properties. Here, first of all, we must have, this is a copper wire. Copper wire is circulated like this, as I explained in the previous animated presentation. Two ends are connected to the battery. Positive end is given to one end and negative end is given to second end. See the animation in this video. Current is circulated in anti-clockwise. White dot indicates the current, so that it becomes north pole and it becomes south pole. There is flow of, see the arrow mark. So along this direction, we are observing the flow of magnetic lines of forces. So along the length of solenoid, inside the solenoid, along the axis, there is magnetic force. This right side face obviously becomes a north pole. We observed, I explained it. If current passes like this face, right side face becomes north pole. Obviously, contrast to that, the other side becomes this side, left side becomes the south pole of the solenoid. So this is the animated video in which clearly we observe the solenoid. So let us move on to the derivation of the solenoid. Here next we continue our discussion for the derivation of solenoid. So students, so far I shown an animated presentation of solenoid and animated video of solenoid. So then with the help of that one, we go to the derivation of expression for magnetic field at the center of straight solenoid. Magnetic field at the center of straight solenoid. Moreover, here we consider this one is a long solenoid. First, let me find the expression for magnetic field at the center of a straight long solenoid. So look into the animation first of all. Once again, what I explained so far. We consider a cylindrical shaped non-conducting object as a base of solenoid. And then we wound the wires. A current carrying wire is wounded on the surface of the solenoid as coils. So look into it. So we wind at them. So wire goes into the board at first one and come out of the board. So wire goes into the board at the bottom and comes out of the board at the top. Remember, direction is also important, students. At the bottom, the current carrying wire goes into the board, at the top it comes out of the board. And this is connected to the battery. So here this is the wire from top to bottom. So as current is traveling in anti-clockwise direction, so current is as shown in the diagram. Current passes as shown in the diagram. Okay. Because of this, each loop contribute magnetic field along its axis. All the loops together to give a large amount of magnetic field along the axis of the solenoid. Here, wire goes into the board at the bottom and comes out of the board. We are representing into the board at the bottom and out of the board presentation at the top. It shows that the current carrying wire carries the current into the board at the bottom and out of the board at the top. Because of this, there exists a magnetic field and this becomes north pole. I explained already, this becomes north pole and this becomes south pole, and there exists magnetic field along the axis of the solenoid B bar along this direction. We would like to find the expression for that magnitude of the magnetic field along the axis of long solenoid. To find that, we consider some part of length of solenoid. Let PQRS is one part of the solenoid. Consider to determine the value of B. Look into this rectangular part that we consider here. Here this is the rectangular part PQRS that we consider. Here in it we consider the direction PQRS, P direction. Okay. Then dimensions. The PQ, it is a rectangular shape such that PQ and RS are of length A, and whereas SP of length B. Of course, this SP of length B. So to find the magnetic field along the axis of the solenoid, we derive the expression with the help of Ampere's law. This is Ampere's law. Let us consider the equation form of Ampere's law. Line integral of magnetic field along any closed loop is mu naught times the net current passing through the loop. If I naught is net current, here we consider PQRS loop. If I naught is the net current passing through the loop, then line integral of magnetic field integral B bar dot dl bar is equal to mu naught I naught. Let us extend the line integral of magnetic field. That means integral B bar dot dl bar is integral B bar dot dl bar along PQ line, along QR line, and along RS line, and along SP line. This sum of these four B bar dot dl bar along sum of these four lines gives the total integral of B bar dot dl bar in closed loop. So let us consider it now. So integral B bar dot dl bar means, look into the first point. Integral B bar dot dl bar along PQ line, then QR line, second step. Third step along RS line, and fourth step along SP line. Sum of B bar dot dl bar along four lines gives the line integral of magnetic field along closed loop. Next one. Now consider the first point, integral B bar dot dl bar along PQ line. We assume B bar along this direction. See the direction of arrow mark. B bar along this direction from left to right. So length direction and B bar direction are parallel. For PQ line, length direction and B bar direction are parallel. So angle between them becomes 0 degrees. So integral B bar dot dl bar cos 0 comes to QR direction. QR is along vertical. QR line is along vertical, whereas B bar is along horizontal. So angle between B bar direction, see the B bar direction and QR direction, these are mutually perpendicular to each other. Therefore angle between QR and B bar is 90. So second step becomes line integral B dl cos 90, expanding dot product. Third one, for RS is a line of the loop which is outside the solenoid. I repeat, RS is a line of the considered loop which is at outside the solenoid. This is important. Outside the solenoid, at this position, there is no magnetic field. That's why for the third step of line integral along RS, B is equal to 0. See this derivation. We put 0 here in place of B. Comes to the fourth one, SP. For SP line and magnetic field, one side perpendicular. Magnetic field is along horizontal, SP is along vertical. So angle between B bar and length is 90. So line integral B dl cos 90. I hope you followed. This is a very crucial step to continue the derivation. So along PQ, theta is 0, B dl cos 0. For QR, theta is 90, B dl cos 90. For RS, there is no magnetic field, so it is 0. For SP, theta is 90, integral B dl cos 90. And we continue it. Then, see the next step. Therefore, this term is cos 90 0, as B 0, third term 0, as cos 90 0, fourth term 0. So, last three terms becomes 0. Therefore, we have only first term. That is B line integral dl. For the line integral dl along PQ. B is constant. So along this line, B is constant for each and every part of this line. That's why we kept B outside the integration. B integral dl. Integral dl means total length of PQ. Total length of PQ is A. Here this is A. So BA. So in Ampere's law, we calculated left side part of the equation. So far, we calculated the left side part of the equation in Ampere's law. Students, observe it. We calculate left side part. Integral B bar dot dl bar of closed loop, line integral of magnetic field along closed loop, determined, and it becomes B into A. Next one, the left hand side is calculated. Now we have to find right hand side. Mu naught is a constant, I naught is the net current passing through all the loops present inside the considered loop. Here we consider PQRS as the closed loop. Inside the loop we have so many current carrying loops. Inside the considered element we have so many current carrying loops. The net current through all the loops is counted as I naught. Remember it, students. I naught is the net current followed by all the loops in the considered element, PQRS element. So here we have to assume small n are the number of loops per unit length. This is the important data that we are considering now. Students, small n, to continue the derivation, this is a very crucial line. Small n is the number of turns per unit length. Okay, what is the length of this element A? So, number of turns per unit length is n, then number of turns per length A. We consider a element of length small a, then number of turns present in a part of length A is n into A. Then each loop, these are the number of turns. In each turn we assume I current is passing. So total current present inside the considered element, closed element is Na into I. So that's why I replace mu naught I naught is equal to mu naught, according to my explanation, I naught is NAI. So replace it mu naught NAI. This is the RHS of Ampere's law. Students, I repeat this explanation. Let us assume small n are the number of turns per unit length. Here I am writing because it is very important line in this derivation. So number of turns per unit length. This is very important term. That's why I am highlighting for the solenoid. Number of turns per unit length of solenoid is the important data about the solenoid. Let small n be the number of turns per unit length of given solenoid. Then for the length A of the closed loop consider here, the total number of turns is equal to Na. In each loop I is the current passing, then total current passing inside the considered element PQRS is total number of turns into current through each turn, so NAI. Then right hand side expression of Ampere's law, mu naught I naught. Here this is the right side expression, mu naught I naught becomes NIA. Now equate, this is the LHS part, that is B into A, RHS part mu naught NAA. Equate them in Ampere's law. Therefore, we get, when you equate these two, here LHS part is BA, okay, LHS part is BA, RHS part mu naught I naught value is mu naught into, that is the expression NAI. So we cancel A, B is equal to mu naught Ni. Students, the magnetic field along the axis of long solenoid is irrespective of the element or part of length that what we consider here to derive the expression. So A get cancelled, A removed ultimately. So the magnetic field B, I am explaining about this expression. B is the magnetic field along the axis of long solenoid is equal to mu naught Ni, where mu naught is permeability of free space, which is equal to 4 pi into 10 power minus 7 SI units. N are the very important term belongs to solenoid. Small n are the number of turns per unit length. Current passing through each turn of the solenoid is I, then B is equal to mu naught Ni. So I repeat, magnetic field along the axis of the solenoid is a long solenoid. Magnetic field at the center of a straight long solenoid is B is equal to, magnetic field at the center of long straight solenoid is B is equal to mu naught Ni, where N is the number of turns per unit length, I is the current passing through each turn of the solenoid. So this is the very good derivation of a solenoid. So let us move on to the magnetic field of a solenoid of finite length. So in the previous part of the video, just we completed magnetic field due to long solenoid at the center. Now this is the important point. Students, we are finding magnetic field of a solenoid of finite length. Okay, see this one. Here let this be a solenoid. So I made the animation. So what we discussed so far, either in animation presentation or animation video or the derivation, for any solenoid basically we have a cylindrical non-metallic structure over which a number of lines turns are wounded. Let this red line indicates the axis of the solenoid. Exactly through the midpoint we have the axis shown by the red line. And we would like to find the magnetic field at some arbitrary point P. Let P be any arbitrary point inside the finite length solenoid. Here this is the finite length solenoid. We assume an arbitrary point P inside the solenoid. Our aim is to find the magnetic field at some arbitrary point P inside the solenoid, and this is the perpendicular distance, and this is also known as the radius of solenoid. Let this radius of the solenoid be R. So we consider solenoid of radius equal to R. Radius of solenoid is equal to capital R. Now this line length equal to radius of solenoid. Now to find it, first of all we have to draw lines to the two extreme ends of the solenoid from arbitrary point P. See, this is the first line drawn from arbitrary point P to the extreme end, and let this angle be pi 1. The leftmost extreme end of the solenoid makes pi 1 angle with arbitrary point. The rightmost extreme end connecting by this line, let this angle be pi 2. This is pi 2. Pi 1, pi 2 are angle made by the arbitrary point P with two extreme ends respectively at left and right sides. To find this, we have to consider some arbitrary position of solenoid. So let arbitrary position of solenoid, let this be the Q be the arbitrary position of solenoid, which is making angle pi with vertical. All angles are considered with respect to vertical line drawn at point P along the radius. With that, the leftmost end makes pi 1 angle, rightmost end makes pi 2 angle. These are the two limiting angles. Pi 1, pi 2 are two limiting angles at left side as well as at right side. We assume some arbitrary part of solenoid at point Q. That Q makes pi angle. Let its distance be x. Distance of Q is x. This is also equal to x. This is x. And this arbitrary point makes pi angle, which is at a distance, horizontal distance x from point P. And at that x, consider some number of turns of solenoid in very small element. We assume very small element of the solenoid at position x, which is at horizontal distance x. So let us see, that is the point. So once again, see the animation. You identify some number of turns. We consider small element of solenoid at that point Q. So the width of this element is dx. Width of this element is dx. This width is dx. At a distance, horizontal distance x from point P, we consider one element on the surface of the solenoid which is in a small length dx. Okay, then we would like to find the magnetic field due to small element. So as usual, small n are the number of turns per unit length. Small n are the number of turns per unit length, which we consider in the previous derivation also. Always we refer small n as the number of turns per unit length of solenoid. Then current confined in it. So the current confined passing through the element, current passing through the element is equal to Ni, where I is referred to be current through each turn of solenoid. Current through solenoid means current to each turn of the solenoid. If I is the current through each turn of the solenoid, then net current present in all loops together, all turns together, is N I into dx. Because N are the number of turns per unit length. If N are the number of turns per unit length, then number of turns in dx length becomes N dx. If dx is the length, if small n are the number of turns per unit length, in length dx total number of turns is equal to N dx. Total number of turns N dx, then total current passing through all the turns of the considered element is I naught, let it be equal to Ni into dx. Then first of all I would like to write magnetic field only due to the element. Magnetic field only due to this element at point P. Then by integrating we find the magnetic field due to all the solenoids. So magnetic field due to only this element at point P, let it be dV. This is equal to mu naught by 4 pi. Mu naught here magnetic field due to current carrying circular coil, mu naught Ni r square by 2 into r square plus x square whole power 3 by 2. So we use that formula, mu naught Ni r square by here mu naught Ni r square by here just I eliminate it. Here I write with the help of that formula mu naught Ni r square, magnetic field due to current carrying circular loop along its axis is mu naught Ni r square by 2 into r square plus x square whole power 3 by 2. So I write that formula. dV is equal to mu naught number of turns Ni, number of turns N dx. Mu naught number of turns in the consider this white shaded loops, white colored loops are the number of turns present in the element dx. So mu naught number of turns in the considered element is N dx, mu naught N I current through each loop, mu naught Ni current through each loop. So we consider directly as N I dx or like this N dx. Mu naught Ni r square, r is the radius of the loop. Already we assume r is the radius of the mu naught Ni r square by 2 into r square plus x square, r square plus x square whole power 3 by 2. So I hope you followed this formula, mu naught Ni r square by 2 into r square plus x square whole power 3 by 2. So let us consider this PQS is a right angle triangle. In right angle triangle PQX S where 90 degrees is there, at S we have 90 degrees. Consider tan pi. Tan pi is equal to x divided by, this is r, this is radius, x by r. On cross multiplying we get x is equal to r tan pi. Differentiate this equation with respect to x on both sides. We find dx is equal to r into secant square pi d pi. Dx is equal to r secant square pi d pi. Let it be equation 2. And this is equation 1. Then find denominator, r square plus x square. Let us consider r square plus x square. X square is r square tan square pi. So r square plus r square, x square value, I am writing x square value. X square value is r square tan square pi. From this r square get common, r square into 1 plus tan square pi. 1 plus tan square pi is secant square pi. So r square plus x square is equal to r square into secant square pi. This is the value of r square plus x square. Let it be equation 3. So we calculated the values of dx here, which is r secant square pi d pi, as well as r square plus x square value, which is r square secant square pi. Substitute the second equation and third equation in first equation, so that we get dB is equal to mu naught ni r square into dx r secant square pi d pi whole divided by r secant square pi d pi whole divided by 2 into here r square plus x square value is r square secant square pi whole power 3 by 2. This is equal to mu naught ni r square into r, that is r cube, into secant square pi d pi whole divided by 2 r square secant square pi whole power 3 by 2 becomes r cube secant cube pi, r cube secant cube pi. R cube get cancelled in numerator and denominator, and secant square pi cancels with 1 secant square pi, there is secant pi. Therefore dV is equal to mu naught ni by 2 into 1 by secant pi. Students, secant square pi by secant cube pi means 1 by secant pi. 1 by secant pi is cos pi. So cos pi d pi. This is magnetic field produced only by the small element of length dx considered at a distance x at point P. But we have to find the magnetic field caused by total solenoid at point P, total solenoid. For that we integrate the equation, then total magnetic field is integral dB. Integral dB to get the magnetic field due to the entire solenoid, and to extend the magnetic field caused by the element to entire solenoid, we change the limits of pi from minus pi 1 to plus pi 2. On left hand side minus pi 1 and right hand side plus pi 2. So when we extend the limits from minus pi 1 to minus pi 2, it becomes the magnetic field due to entire solenoid at the considered point P. So pi value changes from pi is equal to minus pi 1 to pi is equal to minus pi 2 integral dB. So in the integration of above expression, kept constant outside the integration, so that we get mu naught ni by 2 integral pi changes from minus pi 1 to pi changes to plus pi 2, pi changes from minus pi 1 to plus pi 2 of cos pi. You know that integral cos pi is sin pi, and substituting the limits sin pi 2 minus sin of minus pi 1. So minus of minus sin pi 1, that becomes plus sin pi 1. By substituting the limits, we get an ultimate expression B is equal to mu naught ni by 2 into sin pi 1 plus sin pi 2. This is the expression which gives the magnetic field due to solenoid of finite length, that makes angles pi 1, pi 2 with left and right extreme ends with the arbitrary point P. If you have a solenoid of finite length in which leftmost extreme end makes pi 1 angle with arbitrary point P, rightmost extreme point makes pi 2 angle with arbitrary point P, then magnetic field of the entire solenoid at point P is mu naught ni by 2. This is the expression, mu naught ni by 2 into sin pi 1 plus sin pi 2. Terms, mu naught constant, n number of turns per unit length. It is a very important term in solenoid. I is the current passing through each turn of the solenoid, and pi 1 with respect to the point P at which we are finding a magnetic field due to the entire solenoid at this point, at this particular point. If the position of the point changes, B also changes because pi 1, pi 2 changes. Position of the point at which we are finding the magnetic field changes, pi 1, pi 2 changes and magnetic field changes. At particular point P, along its axis at which it makes pi 1 angle and pi 2 angle with two extreme ends. The magnetic field at that point P, the entire solenoid is given by mu naught Ni by 2 into sin pi 1 plus sin pi 2. Students, regarding solenoid, already we derived the expression for magnetic induction due to finite length solenoid at some arbitrary point along its axis. So let us consider the solenoid. So it is a cylindrical structure around which a wire is wounded, and let this be the axis. This red line indicates the axis of the solenoid, and R is the radius of the solenoid, and we would like to find magnetic field at some arbitrary point P. If this point P makes pi 1, pi 2 angles with two extreme ends of the solenoid, we calculated already B is equal to mu naught Ni by 2 into sin pi 1 plus sin pi 2. Mu naught Ni by 2 into sin pi 1 plus sin pi 2. Where n are the number of turns per unit length, this is the very important term, number of turns per unit length. I is the current passing through each loop of the solenoid. Pi 1, pi 2 are angle made with two extreme ends of the solenoid with respect to this arbitrary point P, then magnetic induction at that point P, mu naught Ni by 2 into sin pi 1 plus sin pi 2. Now we conclude some particular cases. First one is magnetic induction due to, this is the first case. We would like to find out magnetic induction due to solenoid of infinite length along axis. When you consider infinite length means long solenoid. So for long solenoid we extend the length of the solenoid to very large value, then angle made, this here if you assume the angle made by the solenoid with two extreme points like this, and these are the angle made with two extreme ends. When consider long solenoid, these angles are considered to be 90, each angle is considered to be 90 for a long solenoid. Therefore, we have to consider that pi 1 is equal to 90 degrees for long solenoid as well as pi 2 is equal to 90 degrees. Substitute these two values in the above equation. Sin 90 1 plus sin 90 1. Therefore, B is equal to mu naught Ni by 2 mu naught Ni by 2 into 1 plus 1 sin 90 plus sin 90 1 plus 1, 2 get cancelled. For a long solenoid at a point inside the solenoid, for long solenoid at a point inside the solenoid and its axis is given by mu naught Ni. Already we derived this expression and we concluded that expression as one subcase of finite length angles. By changing the angles with proper values we find B value. Comes to next case. Here the magnetic induction of solenoid of infinite length at one end. Magnetic induction due to solenoid of infinite length at one end. So let us consider it is at infinity at left end. Let us assume that the solenoid be of infinite length at left end. So pi 1 is considered to be 90 because it is infinite at the left end, pi 1 is 90. This P now shifted to this point. Let us consider the point as P dash here. Then at one end the angle made is considered to be 90 degrees because it is long. We assume long solenoid at left end, and at pi 2 at P dash the pi 2 becomes the 0 degrees. Pi 1 is 90 and pi 2 is equal to 0 degrees. When we locate the point to find the magnetic field at one end of long solenoid, though it is long solenoid, but we are considering magnetic field at one end, then other end is making 90 degrees angle, whereas the same end is making 0 degrees angle. Therefore, substitute the two values of pi 1 and pi 2 in the actual formula of finite length, that is mu naught Ni by 2 into sin pi 1 sin 90, that is 1, sin pi 1 plus sin pi 2 is 0, that is equal to mu naught Ni by 2. Students, let us observe the difference between these two formulae. If you have a long solenoid, magnetic induction at a point inside the solenoid on its axis is mu naught Ni, this is the formula, whereas for same long solenoid, magnetic induction at one end of the solenoid becomes mu naught Ni divided by 2. So, let us come to next case. Magnetic induction, students, let us look into this next case. Magnetic induction due to solenoid of finite length at one end. Here this is the solenoid of radius r and this is the axis of solenoid. Here we would like to find magnetic induction at one end. So let us consider L is the length of the solenoid, R is the radius of solenoid, it is in cylindrical structure. We would like to know the magnetic field at this point P dash at one end. Then we replace pi 1 and pi 2 with the proper values. This is pi 1 and for this pi 1 angle, here sin pi 1, we have to replace sin pi 1. Sin pi 1 is opposite side by hypotenuse. Here hypotenuse, because this side is of length r and this is of length L, the hypotenuse in this right angle triangle is square root of L square plus r square. So that sin pi 1 becomes opposite side is L, sin pi 1 opposite side by hypotenuse, L by square root of L square plus r square. Whereas pi 2, as I explained in previous case, when you consider one end, at one end pi 2 is 0 degrees, at one end the pi 2 becomes 0 degrees and sin pi 2 is 0. Then already we know that the magnetic induction due to finite length solenoid is given by mu naught Ni divided by 2 into sin pi 1 plus sin pi 2, mu naught Ni by 2 into sin pi 1 plus sin pi 2. Therefore, mu naught Ni by 2 into sin pi 1 is L by square root of L square plus r square plus 0, sin pi 2 is 0. Hence, this is the final expression, mu naught Ni by 2 into L by square root of L square plus r square is the magnetic induction due to a solenoid of finite length L and radius r at one end, where n refers to number of turns per unit length. So this is the discussion of solenoid. So students, I just summarize all the expressions belongs to solenoid. If solenoid of infinite length, that is long length, the magnetic induction at a point inside the solenoid of long solenoid on its axis is mu naught Ni, where n are the number of turns per unit length. Okay. If you consider solenoid of finite length and magnetic induction at point P, arbitrary point P, which makes pi 1 pi 2 angle with vertical at two extreme ends are making pi 1 pi 2 angle with vertical, then magnetic induction given by this formula mu naught Ni by 2 into sin pi 1 plus sin pi 2. For long solenoid at one end mu naught Ni by 2, for finite length solenoid at one end mu naught Ni by 2 into L by square root of L square plus r square. Here the small n is the very crucial term in the solenoid, which is known as number of turns per unit length. By knowing its value, we find magnetic field of solenoid at any length, at any position of any length. So later in coming part we discuss the problems belongs to solenoid. Let us move on. Let us move on to the toroid. So we have toroid. So let us move on to that. We continue the toroid for some time. Here It is a tube-like structure. A tube-like structure. Here a current carrying wire is surrounded around the tube. Let us observe the animation in which you are observing a toroid is a tube-like structure, and a current carrying wire is wounded around the tube. When current is passing through it, the magnetic field is acting inside the tube-like structure as shown in the green shaded arrow marks. So this is a toroid. Let us look to the video in which we observe the toroid. Here, this is the video. Here you are observing some part of toroid. Here this is the copper wire. Let us assume it is like a solenoid. This part what we are observing is solenoid. If solenoid is extended for the total tire or total tube, it is a tube-like structure. You can understand the shape of the tube. If this is the finite length solenoid, and if this solenoid is continued along the tube, it becomes a closed loop. Hence, the shape becomes a toroid. In toroid, the magnetic field is as shown in the diagram. See the video. Students, you are observing, we are extending the solenoid along the tube, and it becomes now, it closes the tube and it becomes toroid. In toroid, the green lines shows the direction of magnetic field, and this red lines shows the direction of flow of current. So once again, I would like to show the video. Once again, you observe, when you extend the solenoid along the tube, it becomes a toroid, and there is a magnetic field inside the tube in circular path. So here, let us observe the video. When solenoid is extended along the surface of the tube, it forms a closed one and it forms a toroid, and green lines shows the magnetic field of the toroid. Here we would like to find out the magnetic field inside the toroid. That is our next discussion. Here, students, basically as I explained in animation and also in video, the toroid is a tube-like structure. In violet color, you are observing a tube-like structure. So now we are observing the animation. Here we circulated the current carrying wire like this. So at the top it goes into the board. Here students, at the top it goes into the board. At the top it goes into the board. At every top it goes into the board. At bottom it comes out of the board. Let us observe. So once again I would like to show the animation. Here this is the outside structure of toroid, and we circulated a current carrying wire around the tube-like structure for the total tube. So observe the animation which you are observing. So at the top it goes into and it comes out. So here it goes into the tube and it is out of the tube, so that a current carrying wire is circulated. Now it becomes a toroid. Here when you observe, at the top current is flowing in the loop into the board, and from the board it comes out of the board. So in every loop at the top it comes. If you consider at any point, here it is like this. If you consider here, it goes into the board and it comes out of the board here. So for every position the magnetic field is like this. This is the direction of magnetic field. Here I draw a red loop which indicates the magnetic field direction. Here we have to find out the value of here. Let us consider some length dl. We draw a length dl. Here this is the length. We consider one element along the axis inside the toroid. Let it be dl. And the magnetic field, once again I show the animation in which you observe the direction of magnetic field. I draw the magnetic field in the red loop. So at the consider element of length dl, let us look into the diagram. You observe the direction of magnetic field. See the students, this is the direction of magnetic field. So each and every point, if you consider the element here, and B bar and DL bar are parallel. If you consider the element here, this is the direction of B bar and this is the direction of DL bar. So everywhere, if you consider any part of small element of the toroid inside the toroid, magnetic field and length, as I shown here at different points, B bar and DL bar are parallel to each other. So let O be the center of this tube, R is the radius of toroid. O is the center, R is the radius. So at inside point there is no current. If you consider at this location, in this space, we observe no more current. Current is only through this part. So the current carrying wire is circulated on the tube-like structure of the toroid, but there is no more current in this space. So actually at the center of the toroid, no currents means no magnetic field is existing according to Ampere's law. Similarly, here at outside point, let O be the inside point, Q be the outside point. As well as at outside point, outside the tube-like structure, there are no current carrying wires. At outside the toroid, there is also no more magnetic field. Only magnetic field is inside the toroid. As I drawn a red color loop, inside the toroid there is magnetic field. And we have to find out that the magnetic field inside the toroid. Here B not equal to 0 here, let B be the magnetic field. Let us observe at in the free space inside the part as well as outside the part of the tube structure, there are no more magnetic fields. Only within the tube like structure, current carrying loop, inside the current carrying loops, there is fixed magnetic field in the toroid, and we have to find out that magnetic field. Here for that we use the Ampere's law as well. In case of solenoid, we use the same Ampere's law, that is line integral of magnetic field around any closed loop is equal to mu naught I naught. First let me to find out the LHS, then RHS, then we equate these two to find the magnetic field. So I would like to find LHS, that is line integral of B bar dot DL bar. So here already explained number of times in this closed loop, B bar and DL bar are parallel to each other. At each and every point inside the loop, magnetic field and length of the element are tangential, theta is 0 between them. So when you expand the dot product, it becomes BDL cos 0. Cos 0 is 1, so integral BDL. Moreover, B is constant. Here this B is constant in magnitude. So kept outside the integration, B integral DL. Integral DL is the length of this closed loop. Integral DL is the length of the closed loop. So length of the closed loop is equal to 2 pi r, r is the radius. So B into 2 pi r. Once again, integral B bar dot DL bar. Expand the dot product. BDL, angle between B and DL is 0, cos 0. Magnitude of magnetic field is constant throughout its length. At any part of this inside point, B is same in magnitude. So we kept outside the integration. B integral DL. Integral DL means the perimeter of the loop. We consider the DL part here. Integral DL means total length of the loop of radius R. Average radius is R. Average radius of the toroid is R. So integral DL is 2 pi R. B into 2 pi R. This is LHS of Ampere's law. Now comes to RHS. We would like to find mu naught I naught first of all. Here mu naught I naught. Here the current through each loop is I. Let us assume current through each loop is I. Number of turns per unit length is N. Number of turns per unit length is N. What is the total length of this solenoid, this toroid? Total length of the toroid. Toroid is extended from here to here. So for this closed tube-like structure, total length of the toroid is 2 pi r. Then current through one loop is I. Number of loops per unit length is N into total length, that is 2 pi r. N into 2 pi r, the total number of turns. Here this is total number of turns of the toroid. Total number of turns. The value highlighted here in the circle is total number of turns of the toroid. N are the number of turns per unit length. into total length. Total length of this perimeter is 2 pi r. Number of turns per unit length into total length gives the total number of turns. In each turn, that is in each loop, current is I. For all the loops, current is I into total number of loops. Therefore, I into n into 2 pi r. Let it be I naught. Therefore, LHS of the equation is, RHS of the equation is mu naught I naught, where I naught is the total current through the toroid, that is mu naught into n into 2 pi r into I. Now, substitute the LHS and RHS of Ampere's law. This is Ampere's law. We get here, when you equate those two, LHS is B into 2 pi r, B into 2 pi r LHS, RHS is this one mu naught into I naught. We calculated I naught as I into n into 2 pi r. So we cancel 2 pi r on both sides. Therefore, magnetic induction inside the toroid is finally given by mu naught Ni. This is the formula. Where B is the magnetic field inside the toroid. As usual, N are the number of turns per unit length of the toroid. I is the current passing through each loop. So, we find out the magnetic field due to toroid also, and we, in this part of our discussion, we calculated magnetic field due to solenoid and magnetic field due to toroid. So, let us continue the discussion to solve few numericals, students. So, let us consider the first numerical. I would like to summarize some formulas and continue to solve some problems. Finally, magnetic field produced. We have to find out the magnetic field produced. So, here B value. Find the magnetic field produced by the solenoid. Question is solenoid. Is the number of loops is 400 and current passing through on it is 5 ampere. Length of the solenoid is 40 centimeter. Here, small n is the very important term in the solenoid. That is number of turns per unit length. Let n be the total number of turns, L is the length. Number of turns per unit length is n by L. N is equal to 400. L is equal to 40 centimeters, length of the solenoid. So, 40 into 10 to the power of minus 2 meters. 40 10 times. So, 10 power minus 2 becomes 10 power 2 in numerator. Totally 10 into 10 power 2. So, 10 power 3 are the number of turns, 1000 number of turns per unit length. Unit meter are existing. Unit length means unit meter. And current passing through the solenoid is given by 5 amperes. Then magnetic induction along the axis of the solenoid is given by the expression B is equal to mu naught Ni. At inside the solenoid, this is the expression. So, mu naught is given by 4 pi into 10 to the power of minus 7. Mu naught value 4 pi into 10 power minus 7 into number of turns per unit length are 1000. Current passing is 5. Students, 5 into 4, 20. Therefore, in 20 I am writing 2 pi into 10 power 1. 5 into 4, 20 pi. It is rearranged as 2 pi into 10 power 1 into 10 power minus 7 into 10 power 3. The product of 10 powers becomes 10 power minus 3, 10 power minus 7 into 10 power 4, 10 power minus 3, 2 into pi, 6.28. 6.28 into 10 to the power of minus 3 Weber per meter square is the value of magnetic field inside the solenoid. It is a very direct problem. So, comes to next problem. A long solenoid, it is a long solenoid of 200 turns per centimeter. So, number of turns per meter is the SI value, SI unit value. So, it is 200 turns per centimeter means 10 power minus 2 meter. Number of turns per unit length means that unit length is meter. 200 by 10 power minus 2 meter. That is 2 into 10 to the power of 4 meters per meter, number of turns per unit length, small n, 2 into 10 power 4. Carries current I. Magnetic field at center is B is equal to 6.28 into 10 power minus 2 Weber per meter square. SI unit of magnetic field is 6.28 into 10 power minus 2 Weber per meter square. Another long solenoid. So it is compared with another long, let this be the N1 and this is B1. We have another long solenoid has 100 turns per centimeters. So N2, we write 100 turns per centimeter means N2 is N1 by 2 simply. N1 is 200 turns per centimeter, N2 is 100 turns per centimeter, so N2 is equal to N1 by 2 and carries a current I2 is equal to I1 by 3, I1 by 3, I by 3, let it be I1 by 3. The value of magnetic field at the center is B2 is how much? B2 is how much? This is the problem. So for long solenoid at center magnetic field is given by the formula mu naught Ni, mu is constant. From first one to second one n changes, I changes. Therefore B2 divided by B1 is equal to N2 divided by N1 into I2 divided by I1. Okay. N2 divided by N1 is 1 by 2, 1 by 2. N2 divided by N1 is 1 by 2 from this given data. And I2 is I1 by 3. So I2 by I1 is also equal to 1 by 3. Therefore B2 is equal to B1 by 6. B1 is 6.28 into 10 power minus 2 whole divided by 6. So that is equal to 1.046 into 10 power minus 2 Weber per meter square is the value of magnetic field for second solenoid. This is also important problem. So let us move on to the next problem. A thin but long hollow cylindrical tube of radius R carries I along its length. This is the problem, students, this is the problem belongs to Ampere's law. Here this is the Ampere's law problem. A thin but long hollow cylindrical tube of radius R along its length, find the magnetic field of the magnetic field at a distance r by 2 from the surface, A inside, B outside the tube. So students, here we have a hollow cylindrical long current carrying wire, a thin but long and hollow cylindrical tube of radius r. This radius is r, carries current I along its surface. Find the magnitude of magnetic field at a distance r by 2 at inside point. First bit is inside point. At inside point this is hollow, students, this is hollow cylinder. So for hollow cylinder there is no current at inside point. Therefore at any inside point of hollow cylinder magnetic field is 0. Next B bit, outside the tube. Outside the tube at a distance r by 2. At outside the tube the magnetic field is given by the formula B is equal to mu naught. So magnetic field to current carrying wire at any outside point is given by the formula mu naught I divided by 2 pi into R effective from the axis. Mu naught I by 2 pi R effective from the axis. From the axis the distance is here radius is R plus R by 2. So that is mu naught I by 2 pi into R plus R by 2. R effective is R plus R by 2. That is 3R by 2. 2 get cancelled. Then B is equal to mu naught I divided by 3 pi R. Students, we come to end of this discussion of the problems belongs to solenoid. So we here in this part of our discussion we discussed about the solenoid, magnetic field along axis of the solenoid of finite length and long length at midpoint at one end, and we calculate magnetic field to toroid inside it, and we concluded some problems belongs to them. So thank you for watching. Thank you one and all.